Hey folks, what we're going to talk about today is something I like to call the sensational six. The sensational six are six equations that we'll use a lot throughout our study of linear motion. They're really foundational and really key to our understanding of speed, velocity, acceleration, distance, all those concepts. These are equations that will extend even to our study of two-dimensional motion when we get into that, and even throughout really our whole study of kinematics or mechanics, and even a little bit beyond that. And so they're pretty important equations for what we're going to be doing throughout our study of classical mechanics, Newtonian mechanics, and we'll get a lot of use out of them. So it's important that you know what the equations are, and then know how to use them, and maybe even a little bit about how we came up with these equations, where they came from. And so we'll jump into that here today. Now these equations are based on equations that you already have a fair amount of experience with, and those equations are the following. The first one you have a lot of experience with, and it's this one, that speed or velocity is given by the distance an object travels, d, over the time. Distance divided by time. Speed or velocity is distance divided by time. And that's one we've used a lot, and obviously you had experience with even before we started into physics. The other one is a little bit more recent, and it's this, that acceleration is given by an object's change in velocity, delta v, divided by t. And that's an equation we've worked with very recently here over the last couple of days. But really those two equations are what all these equations are built on, combining the two and kind of unpacking them a little bit and manipulating the variables in those equations so they're in a little bit more useful form. These equations we can use to solve just about any acceleration problem we'll work with throughout the year, and so we'll get quite a bit of use out of them. You do not have to memorize these equations. You don't have to memorize their derivations or where we come up with these equations, but you should be able to follow through the manipulations or how we derive them here over the next half hour or so. You will need to know these equations. They will be on your AP equation page. You can put them on your own personal equation page if you want to, but you don't have to memorize them, but you do need to be familiar with them, how to use them, what the variables mean, and then of course how to apply them to solve certain situations. And we'll get an example for each one. One, just to show you how the equation is used, and then two, to further illustrate for you the use of that proper problem-solving format that we discussed the other day. And so without further ado, let's jump into the first of these equations. Okay, so for this first equation, we're going to start off with this. The other day we got an equation that tells us how to get the acceleration of an object, or how to determine the acceleration of an object. And that was this, that acceleration is change in velocity over time, delta v over t. We can expand that equation a little bit, or write out what we mean by delta v. And if we do that, we're going to rewrite it this way, that delta v means final velocity minus initial velocity, or v minus v0. Now that's a little bit different notation than we may have used the other day. The other day we may have been using like S2 and S1, the second speed and the first speed, but a little bit more used or a little bit more recognizable notation would be the notation that's here, V and V0. And what we mean by that is the following. V0, V subscript 0, is the initial velocity, and v all by itself without a subscript at all is the final velocity. Again, v0 is initial and v stands for final. Now the reason we use v0 for the initial velocity is the 0 refers to the velocity when the time is 0. So when you first start an event, you're possibly using a stopwatch or some kind of timer, and when you first start, the time reads 0. So that's the velocity when the time is at 0, or in this case the initial velocity. And then just v all by itself is the final velocity, or the other velocity in your scenario. We can then move the t to the other side, so multiply both sides times t, and of course it would look like this. And then if we isolate the v, or solve this for v so that we have v equals something, we would add v0 to both sides, and then flip the whole thing around, and it would look like this. V equals V0 plus AT. And this is the first of our sensational six equations. Now if you look at that, it's really not anything new. It's the equation, our equation for acceleration, just manipulated in a way that we've solved it for the variable v, the final velocity. And this is very useful for finding the final velocity of an object. It starts at some velocity, v0, and then accelerates, either speeds up or slows down for some period of time. And so that's where we would use that equation. And again, it's not anything new. It's the acceleration equation, just manipulated so it's in a little bit more useful form. Let's look at an equation, or excuse me, a problem where we could use that equation, the first of the sensational 6 equations. And that would be this one. Albert's on a bicycle traveling at 3 meters per second and then accelerates at a rate of 2 meters per second squared for 4 seconds. How fast is the bike moving at the end of these 4 seconds? Why don't you take a minute, see if you can begin to solve that equation using our solve that problem using our proper problem-solving format. And the first thing you would do, of course, is to pull out the given information in terms of our variables. You can go ahead and draw a picture if you want as well, kind of begin to set up the initial part of that problem. So if we pull out the given information, we'd have this, that the initial velocity was 3. Albert was moving at 3 meters per second. He's then going to accelerate a, 2 meters per second squared, for a time of 4 seconds. T equals 4 seconds. And what we're looking for is v, the final velocity. You could then draw a sketch, possibly looks like this. I know yours may not look as nice as mine. You're not a trained physicist artist like me. And you may not have chosen to draw your Albert looking like a ghost with no arms and your bike with the old-timey, old-fashioned big front wheel bike. In any case, here we have Albert moving at 3 meters per second. He's going to speed up, accelerate at a rate of 2 meters per second squared. I do know he's speeding up, by the way, because this is a positive acceleration, so he's going to be getting faster. He does that for 4 seconds, and we're looking for his final velocity, v. V equals question mark. We're then going to draw our line that separates our givens from our work. The next step then would be to write down any equation that I might want to use that's going to help me to solve this problem. And so I go through my list of equations and I start asking myself, what equations do I have that might be helpful? And I come across this equation in my list of equations, v equals v0 plus at. I think this equation would work quite well because I'm looking for v, the final velocity. I know v0, this one here. I know a, the acceleration, and the time. So we then plug into this equation. V0 is 3, of course, 3 meters per second. A is 2 meters per second squared, and t is 4. And now we can begin to work our way through the algebra. 2 times 4 is 8, of course. Meters per second squared times seconds. This seconds cancels with one of these seconds, cancels with this seconds, and I'm left with meters per second. And that's nice now because I can add these two. I couldn't add these two quantities if they didn't have the same units, meters per second in this case. So 3 meters per second and 8 meters per second give us our final answer, 11 meters per second. Notice the box around the answer in the lower right-hand corner, 11 meters per second. So here's our equation, the first of our sensational 6. Here's a fairly straightforward example of where we would use that equation to solve a problem. Let's move on to the second of our sensational 6 equations. Now, we know that the average velocity of an object can be given by this equation, v_av equals distance divided by time. We've worked with that a little bit already last couple of weeks. We also talked about this equation, the numeric average, that we could, if we had 2 velocities, say, and we wanted to get their average, we could add them up and divide by 2. So both of these could be valid expressions for finding the average velocity of an object. However, be careful, the times would have to be the same, and we looked at problems to illustrate that this kind of average only works if the time at which it goes at each velocity is the same. If the times aren't the same, then that skews the average. But in any case, let's work with these two equations, both expressions for the average velocity of an object. So let's take this first equation, this one here, and let's solve it for d. Let's see if we can rewrite this so that we have d equals something. Well, that's not too difficult to do. We would multiply both sides times t and then flip the whole equation around so that it looks like this. d equals average velocity times time. And that's a fairly common expression. We've worked with that. The distance an object goes is its average velocity times time. Now, let's take our second equation, our second expression for average velocity, this one here, and let's substitute it in for v_av. Instead of just writing this as this boring distance equals average velocity times time, let's complicate the equation a little bit. And everywhere we see VAV, let's write this instead. So now it would look like this. D equals VO plus V divided by 2, that whole quantity, times the time. And then let's substitute in for V. What do I mean by that? Well, in the previous equation, we developed an expression that told me the final velocity of an object. If I had an object that started at some velocity and it accelerated, that equation would give me the final velocity. So let's take this V that's right here, and instead of just writing it as V, let's complicate it once again, and let's write what V equals, or another way to express the idea of final velocity. And so let's rewrite it this way. Again, what I've done here is I've substituted, instead of this V, I've substituted in equation 1, V0 plus AT. Now don't worry too much about why you would do that. What I want you to see is that it's possible to do that it is legitimate or legal to do that. Why? Don't worry. We'll get to that later. And actually the why is because I know what equation we're trying to develop or how we're trying to manipulate these equations. Please just see for now that this is possible to do. Then let's clean this up a little bit. Well, we have two V0s here, and so let's regroup those. Instead of writing them as two separate V0s, let's regroup them as 2 V0. So all I've done here is I've combined these two terms and rewritten it this way. For our next step here, let's divide out the 2. And what I mean by that here is in this term, we have 2V0 divided by 2. Now, dividing out this 2 is going to be a little different. I kind of just want to get rid of the fraction form or get the 2 out of the denominator. So I'm going to rewrite the whole thing this way. The 2 divides out or cancels out here, but of course we still have that 2 factor with this term. And so I'm just going to rewrite it as 1/2 AT. So instead of writing it over 2, I'm just going to basically write it as 1/2 that value, or bring the fraction up in front of the AT. Next step here is going to be this. Let's distribute the t. We have this t here outside of the parentheses. Let's distribute the t or multiply t by each of these terms. So v0 times t, and then this term 1/2 AT times t. And what we end up with is this. D equals v0t plus 1/2 AT squared. And that is the second of our sensational 6 equations. Distance, d, equals v0 times t, the initial velocity times the time, plus 1/2 AT squared, or 1/2 the acceleration times the time squared. Again, that is the second of our sensational 6 equations. Now, what would this equation do for me? How would this equation help me? Well, if you look at this carefully, what we have here is the distance an object is traveling, obviously, d, is equal to v0t. And this is the same equation we started with. If you look back up here to the top, distance is velocity times time. However, our object is not traveling at a constant velocity. It starts at this velocity v0 and then it accelerates. And if something accelerates, that's going to change the distance it goes. If it's going faster, then it's going to go further than it would have had it stayed at a constant velocity. If it is going slower, slowing down, it's going to go less distance than it would have gone had it stayed at that constant velocity. And this piece of our equation, 1/2 AT squared, tells us the distance it goes because it is accelerating, either speeding up or slowing down. And so if it's going faster, it's going to go this much further, 1/2 AT squared further. Or if it's slowing down, it's going to go this much less. A is going to be negative, and so we're going to be taking off or subtracting this distance from the distance it would have gone. And so this is the equation that tells us how far an object goes that's traveling at some initial velocity and then accelerates. It goes this far, plus or minus an additional distance because it's speeding up or slowing down. Now, so here's our equation 2. D equals v0 plus 1/2 AT squared. However, this equation does not appear on your AP equation page in this form. We have the same equation in a different form. It doesn't quite look like this. And so let's talk about what it looks like and maybe why there's a difference. What do we mean by D? Well, D for us means the distance an object travels. How far does it go? And how do we figure out that distance? Well, to figure out the distance an object goes, what we do is we take where it is now, its position now, minus where it started, its position at the beginning. And the symbol that we use for position usually is the idea of x. So x minus x0. x0 would be where it started, its starting position when time was 0. And x would be the final position, where it is now. X referring again to placement or position. And so another way that we could write the idea of distance, how far something goes, is x minus x0. Notice here once again that it's always the final minus initial. It's the way we always find the difference between two quantities, final minus initial, or in this case, x minus x0. And so we could rewrite our equation, instead of writing it as d, we could rewrite it as this. X minus x0 equals v0t plus 1/2 at squared. Rewriting that a little bit, or isolating the x by itself, we could add x0 to both sides, and so rewrite it like this: x equals x0 plus v0t plus 1/2 at squared. And this is the way that this equation is written on your AP equation page, which you'll be receiving shortly. It's the same equation as the equation at the top of the page. It's just written in a different form. And honestly, the d equals v0 form, I think, is actually a little bit more useful. Sometimes, if you're trying to find the exact position where an object is now, given where it started, this form of the equation is more helpful. But most of the time, for most of the problems we're going to do, the equation or the form at the top of the page, the d equals form, is actually much more useful. So this is what you'll see on your AP equation page. What I would encourage you to do is when you get your page, write beside this on your page, write it in this form, and get used to using it in this form as opposed to the way it is here. We'll talk more about the actual day of the test and what resources you have, but I think you'll really get used to seeing this or seeing this equation and realizing this is a more useful way to have it. And so again, it's the same equation when you look at it carefully, written in a different way. Either way, this is our equation number 2. Let's now look at an example of where we would use this equation or these equations to solve a problem. Let's look at this. A child is rollerblading along at 2 meters per second when she decides to accelerate at a rate of 1 meter per second squared for 3 seconds. How far does she travel during this time? Why don't you take a minute, see if you can begin to solve this problem, pulling out the variables, pulling out the important information in terms of our variables, and then maybe even drawing a picture to get this set up. So the givens would look something like this. The initial velocity is 2. Our child is rolling along, skating along 2 meters per second. They accelerate at 1 meter per second squared, so A is 1 meter per second squared for a time of 3 seconds. And we want to know the distance that they go. Now looking at this quickly, you might realize that if the child wasn't accelerating, if they stay at 2 meters per second squared and they do that for 3 seconds, they would go a distance of, can you figure that out? If you're traveling at 2 meters per second squared for 3 seconds, how far do you go? Yeah, you'd go 6 meters. And so we know our answer should be greater than 6 meters because the child is speeding up. So that gives us a little bit of a heads up on our answer when we get to that. Let us check and see if our answer is legitimate. We should be getting something bigger than 6 because if the child did not speed up, if they stayed at a constant velocity of 2 for 3 seconds, they would be going 6 meters. Nonetheless, here's my picture. Now you might not believe this or not, but this is not a freehand drawing. This is actually clip art. I know it's, I know the nice drawings, but this is actually clip art of our child skating. So here she is. She's skating along 2 meters per second squared. She accelerates 1 meter per second squared for 3 seconds, and we want to know the distance she travels during this time. Again, the pick between the picture here and the variables I've pulled out, we can pretty well understand this problem. We could erase all of these words, and between these variables here and this picture, have a pretty good understanding of what this problem is asking me to do. Draw a horizontal line separating the givens from my work. And so now we go about trying to find an equation that we might want to use to solve this. And so we go through our list of equations and we ask ourselves, what equations do I have here that could help me? Well, we don't have too many options. One of the options I guess we have is that distance is velocity times time, or that velocity is distance divided by time. There's a d in that equation, but it doesn't say anything about acceleration, so that equation doesn't help me. But I come across this equation on my equation page, d equals v0t plus 1/2 at squared. And it seems like that equation might be just right. I'm looking for distance, d. I know v0, that's 2. I know the time, that's 3 seconds. 1/2 a is 1 meter per second squared, and of course t, 3 seconds. So I should be able to plug into this equation and solve for the distance. And so plugging into that equation, taking these variables here and plugging them into the appropriate places, would look like this. In your work, you need to show this equation. You need to show plugging into this equation. Notice I've kept the units here, but these two steps you must have in your work to get full credit for the problem. 2 meters per second times 3, 1/2, 1 meter per second squared times 3 seconds. Don't forget this squared. And by the way, this squared only applies to the time. It doesn't apply to this whole term. So now, cleaning up the algebra here a little bit. 2 meters per second times 3 seconds is 6 meters. Make sure you look at the units here. 2 times 3 obviously is 6, but meters over seconds times seconds, the seconds cancel, and I'm just left with meters. Now this term is a little bit more involved. I've got 3 squared, so that would be 9. Have to square the units as well, so it's seconds squared. 1/2 of 1 is 0.5, doesn't change the units, meters per second squared. Now I have these two terms to multiply. Of course, the numbers, 0.5 times 9 gives me 4.5, 4.5. And look at the units carefully. Meters over seconds squared times seconds squared. Again, this seconds squared is in the denominator. This second squared is in the numerator, and so they cancel out. I'm just left with meters, which is good because I could not add 6 and 4 and 4.5 if the units weren't the same, but they are meters and meters. We can add those and we're done. The distance she goes is 10.5 meters. Remember before, a few minutes ago, we were talking about this problem. We said if she wasn't speeding up, she'd go 6 meters. She is speeding up. She's accelerating, so she's going to go further. How much further does she go? That's right here, the 4.5 meters. This is the additional distance she travels, 1/2 at squared, because she's going faster. Therefore, our final answer, 10.5 meters. Again, here's the equation, second of the Sensational 6. Please recognize that on your AP equation page, it's different. It is in a different form on your AP equation page. Same equation, written a different way. And then also the proper problem solving format. Let's go on to equation number 3. I like equation number 3. It's actually my favorite of the 3. The development of it I think is kind of fun. To be the mathematical process we go through here is kind of cool. All that being said, let's jump into it. To start with equation number 3, let's start off with our first of the Sensational 6. V equals V0 plus AT. Equation number 1 from our Sensational 6. And just for fun, let's square both sides of that equation. Y, don't worry about Y once again, just that we can do it. We can do anything we want to an equation as long as we do it to both sides of the equation. And so let's square both sides of this equation. Let's square V, and let's square the quantity V0 plus AT. Well, of course, the left-hand side is pretty easy to square. It's just V squared, as we said. The right-hand side is a little bit more involved. It's the quantity V0 plus AT squared. And we can't just square each individual term, the V0 and the AT. There's a process we have to go through when we're squaring a binomial like this. And of course, you know that process. It's called saran wrap. No, wait a minute. That's not it. It's not called saran wrap. It's called wax paper. No, it's not wax paper. It's... shoot, how do we square? Oh, there it is. We square a binomial using a process called FOIL. Get it? Wax paper, saran wrap. I know. Anyhow, we FOIL, which means first, outer, inner, last. And so if you look at this equation here, think about rewriting it, another in parentheses over here. And if I could work with my pen a little bit better, I would try that. Well, what the heck? Maybe I'll try it. Let's see if I could write that here for you. If I can get my tablet to come on. Hold on. Maybe it's not worth it. Yeah, what the heck. Let's give it a shot. And so right here, we're going to have this. It's going to be another V0, hey, not too bad so far, plus AT. Not bad. Kind of proud of myself there. In any case, and so I'm not sure that's all that helpful, but if you think about FOIL process, it's multiply the first two terms. So that's the V0 and the V0. And then you're going to multiply the outer. So that's going to be the V0 and the AT. Then the inner, this AT and this V0. Then the last, that's the L in FOIL, AT times AT. In other words, you end up with this. First, outer, inner, last. AT times AT. A squared, T squared. Let's get rid of this because that's a mess. And then let's see if we can clean up some terms here. Well, if you look carefully here, you can see there's two of these V0 ATs, and so we could rewrite this as this, just simplifying it a little bit, 2 V0 AT. Then the next step, let's move this V0 squared to the other side. So let's subtract this from both sides. In other words, move it to the left side. It's going to look like this. Careful, it's got to be negative because we're subtracting it from both sides. And then this next step, let's do something here that's a little bit strange. Let me go ahead and put it up here on the board. Let me go ahead and put it up here on the slide. And you see if you can see, first of all, what did I do? What's the difference between this line and the line that's going to show up right here? And then, is it legal to do? Mathematically, is this okay? First of all, see what I did. Make sure you recognize what the difference is between this line and this line. And then, is it legal? Is it mathematically okay to do this? Well, no change over here. Here's the change right here, right? This term or these terms right here. And hopefully you recognize what I did. Obviously, literally what I did is I multiplied by 2.5. But what is the effect of multiplying by 2.5? Well, 2 times 1/2 is just 1. I'm just multiplying by 1. And so I didn't really change anything. There's no effect here in multiplying by 1. It's okay to do. It's legal. Why would you want to do that? Well, the reason I did this is because it's setting myself up for the next step in manipulating these equations. I wouldn't expect you to look at this equation here and say, hey, let's multiply by 2.5. No, but now that you've seen it's done, you can see that it's okay to do it. Because the next step is this. Let's factor out a 2 and an a out of both of these terms. Out of this term here, there's a 2 and there's an a. And now in this term, I've introduced a 2. There was already an a. But I can factor out a 2 and an a out of both of those terms. In other words, rewrite it like this. I take the 2a out of here, so that leaves me with this V0 and this t, so that's right here. And if I take the 2 out of here and I take one of these a's, there's still one there. What I end up with is the half is still there, one of the a's, notice it's not a squared anymore, it's just a. I've taken one of the a's out, and I still have the t squared. So now we have this whole mess. V squared minus V0 squared equals 2a times the quantity V0t plus 1/2 a t squared. And that on its own doesn't look like much, but it's a, well, wait a minute. Actually, it does look like something. Look at this term right here, V0t plus 1/2 at squared. Oh my goodness. Do you recognize what that is? That V0t plus 1/2 at squared? That should be familiar to you. V0t plus 1/2 at squared, oh my gosh. That's equation number 2, isn't it? That's distance, or x minus x0. That's the equation we just developed for equation 2. And so really that whole thing, this whole mess inside the brackets, just reduces to d. That is d. That's equation number 2. And there we are, folks. That is equation number 3. And so there it is, equation number 3. V squared minus V0 squared equals 2AD. And if you go back and look at this equation more carefully, you'll notice a couple things about it. First of all, what does this equation not have that the other two did? Take a careful look at this. Look at all the terms. There's a term that's not here, a quantity that's not in this equation that was in both equation 1 and equation 2. You see what it is? Yeah, that's right. There's no time in this equation. Both equation 1 and equation 2 had a t, a time variable, and equation 3 does not. In other words, this is an equation for velocities, acceleration, distances, for objects accelerating, moving at certain speeds, etc., that does not involve time. And the way we arrived at that, again, if you look carefully at what we did, really what we did here is we combined equation 1, v equals v0 plus at, and equation 2, v0t plus 1f at squared. We combined those two equations together, and we factored out the t. This is one equation that basically takes the place of equation 1 and 2. You could, instead of using this one equation, for problems that involve this equation, you could use equation 1, then go back and use equation 2, but that's a lot of extra work. What this equation does is it's kind of a shortcut. It kind of eliminates the need for those two because it's a combination of the two where the time is factored out. We'll use this equation for problems where it doesn't give us any time or it doesn't ask us about time. As a matter of fact, let's look at an example of that. Now, just as with the previous equation, equation 2, it doesn't show up in that form on our equation page. Equation 3 does not show up exactly like that on your equation page either. You won't find this exact equation on your AP equation page. It's in a little bit different form. And just as in the previous equation, it's not written in terms of d, it's x minus x0. The AP equation page substitutes in x minus x0 for d, so it's this. And then it takes another step further and moves the v0 squared to the other side. So it basically isolates the v by itself. Again, it's the same equation. Please recognize that. This term here, x minus x0, is just d. And then we've just moved the v0 to the other side, trying to get this v kind of by itself. This is the form that you'll see on your AP equation page, what's here in yellow. It's the same thing, once again. And honestly, most of the time, I will probably still write it this way. This is the way it's written. I think most of the time, just d, the distance an object travels, is more helpful. And then whether you move this variable to the other side or not really doesn't change it. This is the way it's on your page. When you get your equation page, you'll see that. You may want to jot this one beside it over in the margin because this is probably the way we'll use it more often, the way we'll refer to it. Same equation, different form. So let's look at an example of where we would use that equation. Wow, seeing this problem kind of makes me a little sad. Talking about Mr. Zaccarda. Many of you know Mr. Zaccarda. Many of you had him as a teacher or a coach who's no longer with us here at Simone Wright. You know, he's moved on to another school, and he's a great man. He's a good friend and a huge loss to our school. But by the way, I know from what I understand, he's doing really well. He's settling into his new school. And, not liking the commute and missing all of us, of course, but he's doing good. So anyhow, it makes me a little sad to think about Mr. Zaccarda. But in any case, here's the problem we're going to work with. Mr. Zaccarda is moving at 25 meters per second in his car when he decides to start accelerating at 7 meters per second squared for 10 meters. And we want to know his final velocity. How fast is he going after all that occurs? Why don't you take a minute, see if you can pull out the givens, and maybe even draw a sketch of this situation. Okay, so here's what we have. Mr. Zaccarda's initial velocity was 25 meters per second. He's going to accelerate 7 meters per second squared for a distance of 10 meters. And we're looking for his final velocity after he does that. Here's a sketch of the situation. Hopefully you have something similar. Mr. Zaccarda is traveling at 25 meters per second here. He's going to speed up, accelerate 7 meters per second squared over a distance of 10 meters, not very far, but 10 meters. And we want to know how fast is he going. By the way, because this distance is small, he's speeding up, but he only accelerates for 10 meters. We don't, well, you tell me, do we expect this velocity to be, his final velocity to be a whole lot larger than 25 or just slightly larger than 20? First of all, is it going to be larger or smaller? Hopefully you realize it's going to be larger because he is accelerating a positive acceleration. And yeah, it's not going to be a whole lot larger. He doesn't accelerate for very far. It's only 10 meters. So even though he's speeding up, he doesn't do that for a very large distance. So we don't expect this final velocity to be a whole lot bigger than the initial 25 meters per second. Also notice in this problem, there's no time. It doesn't reference time, doesn't tell me for how long Mr. Zaccarda sped up, and it doesn't ask me to find the time. It doesn't say anything about time in this problem. And that's going to be important in the way we go about solving this problem. So I think in looking at this problem, you'll see that this is the equation we ought to use. It doesn't have time in it, and it's giving me the final velocity here. Here's the initial velocity that we know, the acceleration times the distance. We could use the first equation and the second equation combined, solve one for some variable, plug it into the second equation to find our final time. But that would be well, not difficult, just a couple added steps. And so this equation really just saves us the work and having to do two separate equations, and it just solves it all in the form of one equation. We can now plug into this equation. It looks like this. Here's our terms that we plugged in. Here's V0. Here's my A. There's my distance. I'm now going to go about doing the algebra. So on this side, 2 times 7 times 10 gives me 140. On this side, 25 squared, 625. Also pay attention to the units. Squaring meters per second is going to give me meters squared second squared. And over here, it's meters times meters over second squared, or again, meters squared second squared. So first step of algebra would look like this. Again, notice the units, and notice the units are the same, meters squared second squared. And that then allows me to do the next step. We would add 625 to both sides. We could not add these two terms if they weren't the same units. Just can't do it. But they are. 625 plus 140 gives me 765. Careful. One of the common errors with this equation, or use solving problems this way, is some people forget to take the final square root. This is v squared. What we want is v. Another hint that could be an issue is the units don't look right for a velocity. The units are meters squared second squared, and velocity units are simply meters per second. So in taking the square root, we end up with this. The final velocity is 27.7. And we would put a box around that answer and write it in the lower right-hand side of our problem over here like this. One of the hints, another hint, by the way, that this would not be our final answer. The velocity is way too fast. Mr. Zaccarda didn't go from 25 to 765 meters per second in a distance of 10 meters. That acceleration is not great enough, and this would not even be a reasonable speed for any car. Again, taking the square root, make sure you do that. That's a common error with this equation. Okay, moving on to the next equations. Now, before we do that, let me pause here. I realize you may have a concern. You're saying to yourself, well, Mr. Gerard, these equations are cool. The problems we've done, or the example problems we've done, have been very helpful of these. However, these three equations have taken pretty long. I mean, they've probably taken us, I don't know, 20 minutes or so to do just these three equations. Does that mean that there's going to be another 20 minutes, twice as long, to do the next three? And that would take a long time, and I'm a little concerned about taking that much time. Well, fear not, my friends, because these next three equations will actually go a lot faster than the first three. If we set the initial velocity of our condition, of our situation, to be 0, and look at the first three equations. In other words, if V0 is 0 in our first three equations, here's equation 1, V equals V0 plus AT. Here's equation 2, D equals V0T plus 1F AT squared. And here's the third one, V squared minus V0 squared equals 2AD. If the initial velocity is 0, so if this term is 0, if this term is 0, and if this term is 0, then that really changes things. Look at equation 1, this one right here. If V0 is 0, this whole term drops out, and it simply becomes this, V equals AT. And that, my friends, or that, get it? That V equals AT, that is equation 4. There it is, right there, V equals AT. Equation number 4, Sensational 6, equation number 4, right there. Take a look at equation number 2. D equals V0T plus 1F AT squared. If V0 is 0, then this is 0, but of course 0 times T, or 0 times anything, is 0, and so we lose this whole term, and we're simply left with that one. Here's equation number 5. D equals 1/2 AT squared. It's second equation, equation number 2, where the initial velocity is 0. D equals 1/2 AT squared. Equation number 5. And going on to the last one then, V squared minus V0 squared equals 2AD. If V0 is 0, that would be this term here. Then that whole term goes away, and we're left with this. Here is equation number 6. V squared equals 2AD. Here's equation 4, equation 5, equation 6. And what these are really are simplifications of the first three equations. Now, None of these equations show up on your AP equation page. They're just not there. And that's okay. We're still going to use them, and I think you'll find them very helpful. Can you do the problems that we're going to do without these equations? By all means, you can. You're just going to be using the longer form, equation 1, 2, and 3, and that would be okay. It's just that many times these simplifications save you a little bit of work. But I already want to caution you, okay? Be careful in using these equations. You can only apply them in certain situations and only at those times, and you need to use them carefully at those times. And what are the times where you can use these three equations? Well, you can only use these three equations if V0 is 0. In other words, if the initial velocity is 0. That's the only time you can use these equations. And so what I would encourage you to do as you write them down is write them in a special little section of your equation page. If you're writing them on your AP equation page at some point, maybe you put a little box around them. And beside the box or that section, wherever you write them, I would write these words or something similar. Only use, or if and only if, V0 is 0. And maybe put a little asterisk or use some color coding or something to remind yourself of that. These are very, very useful equations, and there are many conditions or many situations where V0 is 0. But you can only use these three equations if that's the case. Again, they're not on your AP equation page. You won't have them actually the day of the AP test, but you can use them, and you'll probably remember them. Maybe even when you get your equation page, you write these in beside these three equations just as an additional help. And by all means, you can do that. We'll use them. We'll practice with them. But again, they're not already there. Okay, so let's look at some examples of where we could use these three equations. We'll do one problem for each of the three. Let's start off with this. A bullet is shot from a musket with an acceleration of 300 meters per second squared and accelerates for 0.08 seconds. What is the final velocity of this bullet? So let's pull out some given information or some important information. Well, one of the pieces of information you might see, one of the important pieces of information you may pull out of this is the idea of the acceleration. Okay, the bullet is shot, it accelerates at 300 meters per second squared. And the time, it accelerates for a time period of 0.08 seconds. Not a very long period of time. Remember, we're talking about a bullet here. It's shot very fast, it speeds up very fast, and the time intervals are very small. We're looking for the final velocity. Here's the question. Is there any other information you'd pull out of here? Anything else that you might see as important? Hopefully you do, because it's really important to the problem. However, it's not a number. And it actually doesn't even say this explicitly. You must imply this. And what I'm getting at here is this. When you shoot a bullet from a gun, what is its initial velocity? Yeah, that's right. At the instant you pull the trigger, its initial velocity is 0. It's not moving yet, but it is accelerating. And so that's really important to see in this problem, that the initial velocity is 0. Again, it doesn't explicitly say that. You must read that into, you must infer that in this problem, and that's absolutely correct and essential to be able to do that in this kind of problem. V0 is 0. It doesn't explicitly or literally come out and say V0 is 0, but that's an important piece of information that you must glean from this problem in order to be able to solve it correctly. And we'll look at other situations like this. There's some common situations where V0 is 0, but it doesn't explicitly say it. And then we'll draw a picture of the situation. Once again, I cheated, I used clip art, but here's our person shooting the bullet. V0 is 0, so the bullet's here in the gun. It's not moving at the instant it's shot. It's here in the gun. It's not moving at the instant you pull the trigger. It is accelerating. It's getting faster. It just hasn't started moving yet. Accelerating 300 meters per second squared for 0.08 seconds. Only the time is traveling in the barrel, so a very short time. And we want to know what is its speed right here when it leaves the barrel. What is its final velocity after it's done accelerating. So now we go look at our equations, and we have a couple options here. We could use the very first equation, V equals V0 plus AT, and just plug in the 0 and go from there. However, I think it's a little simpler just to jump to using this equation, or that equation, I love it, and plug in. Equation number 4 is what I think I would use. Plugging in then, the acceleration 300 meters per second squared, the time 0.08 seconds, 300 times 0.08, and then of course the units, meters per second squared times seconds. Make sure you're doing the algebra with the units. And cleaning this up then, we get a speed of 24 meters per second. V equals AT, proper format, final answer, lower right-hand corner of the problem. Let's look at another. A bullet is shot from a musket with an acceleration of 300 meters per second squared and accelerates for 0.08 seconds. How far does the bullet travel in that time? In other words, the length of the barrel is really what it's asking. Once you take a second, see if you can pull out the given information, maybe even draw yourself a little picture, and then we'll run through it together. So here's our givens. Once again, we have to recognize that V0 is 0. I notice a typo there. That should be V0 right there. It just says V, but that should be V0 is 0. Accelerate 300 meters per second squared, time 0.08 seconds, and we're looking for the distance that it travels. Here's our picture. Very much the same picture. The difference here is now we're looking for the distance it goes rather than the time, but it's a similar kind of situation. Here's the equation I would use. Again, we could use the longer form of this equation, d equals v0t plus 1/2 at squared. I'm going to choose to use equation 5. It's just a little simpler. And so now plugging into that equation, plug in your a, plug in the t squared or the time for t squared. I'm not sure why this format did this. I guess, but in any case, here's my a, here's my t. 300 times 0.08 squared. Don't forget you need to square the 0.08 seconds. Next up, algebra. Actually, I skipped that algebra, and here's my distance, 0.96 meters. Almost a meter long is telling me this barrel is how long or the distance for which it's accelerating. There's equation number 5, proper format, final answer, lower right-hand corner, 0.96 meters. And here then is our last and final example. A runner takes off the sound of a pistol and accelerates 2.1 meters per second squared for 20 meters. What is his velocity? First thing you're going to want to do here is pull out the given information and then draw a sketch of the situation. Give you a second to try that. Hopefully you recognize as you do that V0 is 0, and that's an important part of this problem. Once again, a typo here, that should say V0 right there. And so in your notes, if you're writing this down, make sure you write it as V0. The final velocity is not 0. That would be kind of an unfortunate race or kind of a useless race if the final velocity is 0, if the runner never goes anywhere. But V0 is 0. This is another situation where the initial velocity is not literally said to be 0. You must imply or infer that. That's a pretty common situation, something taking off at a race or something starting from a stop sign or something like that. Bullets being shot, things taking off, maybe when you drop something would be another case like that. When you drop a ball, its initial velocity is 0. All those are cases where it's probably not going to say the initial velocity is 0 or starts from rest. You're going to need to infer that or imply that in the problem. Here's our runner taking off then. Taking off, starting 0, they're going to accelerate 2.1 meters per second squared for a distance of 20 meters, and we want to know the velocity at the end of that time. Here's the equation I would use. V squared equals 2AD. Again, you could use the longer form of that, plug in 0, and eventually you're going to end up at the same place. So why not just start here, save yourself a little bit of work. Plugging into that, the acceleration 2.1 meters per second squared, distance of 20 meters, crunch through the algebra. You get 84, and again, notice the units here, meters squared second squared, that's V squared. Two reasons you would notice here that this is not your final answer. First of all, the units don't work right for speed. Meters squared second squared are not the correct units for speed. And secondly, 84 meters, even if this was meters per second, 84 meters per second is way too fast for a runner to be running. It just wouldn't be possible. It's not a plausible answer. Taking the square root of both sides, we get a much more reasonable answer, 9.2 meters per second. The units are correct. Again, common error here, not taking the square root. Make sure you don't do that. Make sure you finish the problem, take the square root of both sides, and the final answer in a box, lower right-hand corner, 9.2 meters per second. Again, proper format. And the use of this equation, equation number 6.